Observe the mechanical difference. A reciprocating pump on the left pushes water in a straight line. On the right, a centrifugal pump operates by throwing the water outward using rotational speed. Because this relies on velocity rather than displacement, the centrifugal pump is a kinematic engine. It uses pure rotational motion to build fluid pressure. This diagnostic matrix shows the core difference between pump types. Centrifugal pumps give a smooth, continuous flow and handle dirty or viscous fluids like mud. Reciprocating pumps produce a pulsing flow, strictly for clean fluids, but generate exceptionally high pressure. So how exactly does a centrifugal pump maintain that high-volume, continuous output? The strainer blocks debris, while the foot valve ensures the pump casing stays primed. Inside, the spinning impeller forces fluid outward with immense velocity. Finally, the expanding volute casing applies Bernoulli's principle. As space widens, fluid velocity drops, converting kinetic energy into static pressure. The entire machine functions as a precise two-stage energy converter, first imparting speed, then trading that speed for pressure. And it relies completely on an unbroken, continuous column of fluid to do so. Let's look at this vertical lift diagram to understand the resistance the pump has to overcome. Static head is the absolute minimum vertical height the fluid must be pushed, combining the suction and delivery heights in a theoretical zero-friction universe. In reality, we have to use manometric head. This graphic shows how the true workload stacks up. To find the actual resistance, you have to add pipe friction losses and the exit kinetic energy right on top of that base physical lift. Overcoming that total stacked head requires power, but the electricity fed into the motor is never the exact amount of energy that actually reaches the fluid. This power flow overview tracks the energy. Raw electric input is shaft power. Before blades turn, friction bleeds energy. The surviving ratio is mechanical efficiency. Next, as blades strike fluid, energy is lost to hydraulic shock. The power transferring into the fluid is manometric efficiency. Finally, some of that newly pressurized fluid inevitably leaks back to the suction side through tiny clearance rings, which gives us volumetric efficiency. Multiply these three together and you have overall efficiency, the final ratio of useful water power delivered compared to the raw shaft power supplied. The electrical power you pay for is taxed by mechanical friction, hydraulic shock, and internal leakage long before a single drop of water reaches its destination. Watch for 3 exam traps. 1. Radial entry. Assume inlet whirl velocity is 0. 2. Kinematic conversions. Convert RPM to linear speed using pi dn over 60. 3. Unit mismatches. Formulas yield water power in watts, but shaft power is kilowatts. Divide by 1,000. Let's put this into practice. Read the prompt on this execution slide. We have a 500 mm impeller at 1200 RPM with a 30-degree vane angle. Pause the video right here and try to calculate the work done per kilogram of water. Memorizing fluid mechanics theory won't help your score if you stumble on these unit conversions and missing variables during the actual test. Let's execute the solution. In step 1, we bypass the kinematic trap by using pi dn over 60. This correctly converts our 1200 RPM into a linear blade speed of 31.41 meters per second. In step 2, we set up the outlet velocity triangle using the 30-degree vane angle. By using the tangent function with our flow velocity and calculated blade speed, we isolate the outlet whirl velocity, VW2, at 27.08 meters per second. Finally, in step 3, we calculate the work done by multiplying that whirl velocity by the blade speed. This gives us the correct final answer of 850.5 joules per kilogram. To lock this all down, take a screenshot of this summary matrix. Keep the head stack formula and the overall efficiency multiplier fresh in your mind, and always default to assuming radial entry at the inlet. Mastering this specific sequence, from hardware flow to tracking power losses to identifying unit traps, gives you a complete diagnostic toolkit for dominating the fluid machinery questions on your exam.